Okay, so we have physics paper May June 2013, paper 23. So our first question, state the SI base units of force, which would be force equals ma, and then mass is obviously kilograms, acceleration is meters per second square. So this would be kgms minus 2. Then we have two wires of length L placed parallel, distance x apart. Each wire carries a current I. The currents give rise to a force F. Okay. Where K is constant is determine the SI base units. Okay, so first of all, we make K the subject. So I square L and K. Now, force is going to be kg ms minus 2. X is distance, so it's meters. Current is obviously ampere, so a square, and then length is, again, it's going to be meters. So we can just cancel out the meter, and then just go kg m s minus 2, and then a square above would be a minus 2. Sketch the variation of x, sketch the variation with x of f. Okay, so what is the relationship between f and x? So if you increase x, you will decrease f, which means it's a inverse proportion. So f equals k by x, which means as you increase x, f will also decrease. So the inverse graph looks sort of like this. Kind of like this. It's not really like this. It's like that. Make sure not to touch the axes, right? Because that's how inverse proportion works. This is just a standard graph of inverse proportion. The current I in both the wires is varied. Sketch the relation of I of f. So f is proportional to I square, and so as I increases, f will also increase, but it won't be a straight line graph like that. It'll be curved upwards because that's how x square graphs work. So yeah, okay. And also make sure that it's through the origin. This one's kind of not through the origin. Let me just boom. So like that. Yeah. Okay. So this is a question 2. A student walks from A to B along the path shown in figure 2.1. The student takes time t to walk from A to B. State quantity apart from t that must be measured in order to determine the average value of speed. Distance. Because speed equals distance divided by time. And then velocity equals displacement divided by time. So you'll use displacement. Displacement from A to B. A to B, displacement from A to B. Okay, so define acceleration. Acceleration is just change in velocity per unit time, or rate of change in velocity. It's just the same thing. Okay, a girl falls onto a trampoline. The trampoline consists of blah blah blah. At time t equals 0, the girl starts to fall. Okay. Hits the trampoline, rebounds vertically. The variation with time t of v is illustrated. Okay. So for this is the graph, and then for the motion of the girl, calculate distance forms between t0 and when she hits the trampoline. So evidently she hits the trampoline like around here. This is like what, 0.6, 0.7, 0.8, this is 0.9. So distance is obviously area area under the graph. So half into what is the max speed? The max speed is like, what is this? Like 8.4, 8.8, 8.8, 8.8 into 0.9. So if you calculate that, that is like, what is that? That's 3.96 meters. Or if you obviously go to 2 significant, it's 4.0 meters. The average acceleration during the rebound, okay. Average acceleration during the rebound, so it goes from 8.8 at the top here to like minus 4.4 to the bottom. And this is 1.4 seconds, and it started at 0.9. So total time 0.5. So acceleration equals v minus u over t. So the total change in velocity is like 8.8 plus 4.4, 13.2, and then divide by 0.5. That is going to be 26.4. And obviously you have to put minus, or don't, actually it doesn't really matter, but because it's deaccelerating, velocity decreasing, so just put a minus. It's better. Use figure 2.3 to compare without calculation the acceleration of the girl before and after rebound. Okay, so both of these seem parallel to each other, if I'm gonna be honest. This is her acceleration before, and then this is her acceleration after. But they both seem parallel to me. So you can obviously calculate it. I know they say without calculation, but they mean like not, you can't use calculation in the answer. So if you want to make sure, you can just calculate it. But I'm just gonna like do it off what I can see. So I can see that their gradients are the same because the slope of the line is the same. So acceleration is constant. Same. First of all, acceleration is constant because of straight line. Due to straight line, and then the accelerations are same. They are same because the gradients are the same. Gradients are same. Okay. Use figure 2.3 to compare without calculation the potential energy of the girl at t0 and t equals 1.85. So obviously at t 1.85, because she's falling downwards, right? T 1.85 seconds. Oh, t 1.85 seconds. She's like, huh. Okay, wait. T 1.85 is this, right? So she rebounds vertically, but obviously she doesn't get to the same point because she'll lose energy. So obviously because the area here, right? Because potential energy depends upon the height. And the height that she fell from the top, like from the top to here, the height she fell is given by the area here, like area under the graph. And then the height she rebound is given by this, right? So this is obviously a lot smaller than this, which means that she will have a lot less potential energy at t equals 1.85. The 1.85 potential energy is less because area under graph is the height, and second area is a lot smaller. Second area is smaller. Okay. By the way, you can also do the same thing with kinetic energy instead of potential. Like you could go like um that the first time she was like dropping down, the obviously the potential energy that is lost will be equals to kinetic energy. And obviously she reaches a lot higher kinetic energy because her uh speed is a lot more. Whereas in this, like the kinetic energy she gains is a lot less. So that means that obviously her potential energy is a lot less because the loss in potential energy is less. Okay. State the principle of conservation of momentum. This is simple that for a closed system or for a system with no external forces, for a closed slash isolated system, the sum of momentum before collision is equals to sum after. Sum after collision. The difference between an elastic and inelastic. So an inelastic energy is not conserved, elastic it is. So kinetic energy uh, is conserved. Conserved in elastic collision. Collision. Okay, and then you have two objects, one of mass 4.2, 3.6 velocity, and then 1.5 and 1.2 meters per second. Object B, yeah, the objects collide. Okay, so these two kind of collide, and then both of them move to the right. Okay, object A has v, and object B has velocity 3. Calculate the velocity v of object after collision. So this is just sum of momentum before an object collision. So here it would be times 3.6. This is the momentum of A, and then you have to minus because they're in different directions. Momentum is vector. 1.5 and 1.2 is equals uh to the right, so 4.2 v plus 1.5 times 3. So just calculate this. Um, minus 1.5 times 3, and then divide by 4.2. So we have velocity as 2.1. Okay. Determine whether the collision is elastic or inelastic. Now you could do this two ways. You could do this by checking velocity of separation and velocity of velocity speed of approach and speed of separation. Or you could do kinetic energy. You could check the kinetic energy before and kinetic energy after, but that's the longer way. You can just do it like this. So 3.6 plus 1.2 equals to 3.0 minus 2.1. 3.1? Because relative speed of approach is this, so units per separation is this. So 4.8 equals 3.0 minus 2.1 is 0.9. These two are not equal. Not equal. So this is inelastic. By the way, the formula for this is u1 minus u2 equals V2 minus V1. So if you actually put it in, and let's just take this as U1 and then this is U2. If you put this in, this will give you 3.6 minus, and then because it's in the opposite direction, you'll go minus 1.2, right? So this will just become 3.6 plus 1.2, like over here. And then for V2, so if this is V2, right? We took U2 as B, so we have to take V2 as the speed of B. So 3.0 minus, and then considering they're in the same direction, it's obviously going to be positive V is 2.1, so it's just 3.0 minus 2.1. Okay. Define stress. Stress is just force divided by area, and then strain is just extension over original length. No, length. So, okay. Young modulus, you're given a wire. Young modulus is this. What? Young modulus in the middle is, okay, cross-sectional area of the wire is this, where it's extended by force F. This causes the length of the wire to be increased by 0.095. Okay. Calculate the stress. Alright, so E equals stress over strain. I'm pretty sure you can find the strain, which is because they said that the length of the wire is increased by 0.095%. So length is just plussed by this length of 0.095, and then percent is just 100. So this is the new length, and obviously if you want to find the extension, then you just minus the original one. Minus length. And if you minus L out of this, you'll just get extension as this. 95 divided by 100. So wait, what am I doing? Wait, so strain is equals to extension divided by original length, right? And they told us that the length of the wire is increased by 0.095%, which means that, okay, yeah, okay. So imagine that length is like 1. So for this 1 to be extended by 0.095%, you would have to have the extension be 0.095, right? Or you would have to have it be 0.095 divided by 100. Yeah. 0.95 divided by 100. Yeah. Okay. So to do that, right? You'd have to basically the strain would obviously then be 0.095 divided by 100. This would be the strain, 0.095 divided by 100, right? Because the length is increased by 0.095%. Percent is just a way to say divided by 100. So Young modulus is 0.17 terapascals. Tera is times 10 to the power 12, and then you multiply it by 0.095 divided by 100, and put this equals to stress. Stress, and then the answer is 1.6 times 10 to the power of 8 pascals. Now, if you're actually wondering why, right, so if you're actually wondering why 0.095% or 0.095 divided by 100 is our stress, it's because, like, suppose you have length as 1, right? And you're extending the wire by 0.095%. That means that essentially you're extending it by 0.095 divided by 100 times 1, right? You're extending it by 0.094% of 1. the extension is 0.095%, right? The extension is 0.095% of 1, because that's the original length. And if you calculate this, this is 9.5 times 10 to the power of minus 4 is your extension. And stress is extension by length, and since length was 1, that makes your stress also 9.5 times 10 to the power of minus 4. And this works for any length, because stress is basically a ratio of extension and length. And this is also a ratio, right? A percentage is a ratio. You're increasing something by 0.095% means that the ratio of the extension and the original length is 0.095%. Next is, I guess they're asking you for the force. Now you know that stress is this, and the formula of stress is force over area. And you know that the area is this, so you should multiply by 0.18. But obviously do not forget to divide 0.18 by to convert it into meter square, because you can't use millimeter square because that's not like an SI base unit. So you just convert it first. Divided by 1,000 divided by 1,000. So this area is 1.8 times 10 to the power of minus 7. You multiply by 1.6 times 10 to the power of 8, which is 28.8. So yeah, 28.8. Actually in the marking scheme, it's written that this is 29.1 or 29.0, but that's because they used, the stress here is actually 1.62 or 1.615, so they used that. But it doesn't really matter, because in the newer marking schemes, you'll see that they will usually just ask you to take this instead of the actual answer. And if they don't, then like they'll have both of the answers there. So they'll have like 28.8 or 29. So yeah, that there's nothing to worry about there. Explain the principle of superposition. This is just the same definition that you'll just have to memorize, which is that when two or more waves overlap, the resultant displacement is the sum of individual displacements. The resultant displacement is the sum of individual displacements. Okay. So sound waves travel from source S to a point X along two paths. Okay. State the phase difference between these waves at X for this to be the position of a minimum. Okay. Minimum means destructive interference, and destructive interference must have this kind of a thing. Right. So, oh, sorry. This is not path difference. Sorry. Phase difference. Sorry. So phase difference for destructive interference is 180, and then for maximum, it's either 0 or 360. I was thinking about a path difference. Sorry. So obviously the unit is degrees. So like, I guess just degrees, or like this degrees. Really this, really. This can also be written as like n plus half into 360, because this can literally be anything that's not like full 360. This could be like what this could be like 400 and sorry, not 480. This could be 540 or like basically anything that comes between 0 and 360 and 720, etc. The frequency of the sound from S is 400 hertz and speed of sound is this, so just V equals F lambda 320 divided by 400. That is 0.8. So distance SB is 3.0 and distance PX is 4.0. Angle of SPX suggests whether the minimum or maximum is detected. So first of all, let's try and find SX, which is 5 obviously, because this is a Pythagoras. You can just use C squared equals A squared plus B squared equals C squared. So this is 5, and then to determine whether something is a maximum or a minimum, you use path difference, right? So the path difference, if it's n lambda, then it's maximum. If it's n plus half lambda, or well, n plus lambda by 2 or something. Like if it's 1 lambda, 2 lambda, 3 lambda, it's max, and then if it's like 2.5 lambda or like 1.5 lambda, then it's destructive interference and you'll get a minimum. So the path difference here is one wave is going from here to here, right? So it's going 3 meters here and then 4 meters, so 7 meters. And then one is going 5 meters. So the path difference is difference in distances, which is 7 minus 5, so it's 2. Now our wavelength was 0.8. So 2 divided by 0.8 is 2.5. Which means that this is obviously n plus lambda by 2, which means this will be destructive, which means that it'll be a minimum. Since path difference equals 7 minus 5 equals 2, and then divided by 0.8 equals to 2.5 lambda slash n plus half lambda. Define the potential difference, okay? Potential difference is the work done on charge to wait. Electromotive force and it's no, sorry. It's but it's by charge. When work done by charge. Sorry. From basically work done by charge to convert electric energy to other forms. So like potential differences work done on like components by the charge. EMF is the work done by the battery in making the charge move around. So we have an arrangement, no internal resistance. Okay. Resistance of R2 is 600 ohms and resistance of R1 is 0. Okay, so it's a variable. The maximum potential difference across V2. Okay, so if you put R1 as 0, that means that basically no voltage will be allocated to it, which means that all the voltage will go to R2, so 20, because that's the maximum voltage that can be given. The minimum potential difference across R2. If you put R1 at 400, which is maximum, because basically the greater the resistance, the greater the voltage there will be. So if you put this as 400, let's just do that. Let's just do that. We can do this a couple of ways. I'll just do it a bit of a long way. We can just find the current V by R, so 10 divided by 1,000. So current is 0.02. And then, because you know the current, you can just multiply that by 600 because V equals IR. So 0.2 into 600, you get 12 volts. Okay, a light-dependent resistor is connected in parallel with R2 as shown in the figure 6.2. When light intensity is varied, the resistance of the LDR changes from 5 kilowatts to 1.2. So resistance decreases, which probably means that more light is shown on it, right? Yeah, okay. For maximum light intensity, calculate the total resistance of R2 and the LDR. So for maximum light intensity, it means that the resistance of the LDR must be the lowest because both of them are inversely proportional. More light equals less resistance, and the lowest resistance 1.2. So, and in parallel, you use 1 by R efficient. Effective equals 1 by 600 plus 1 by 1200 is 1.4 kilo ohms. So the answer will be, I believe 1 by 400 ohms. So the resistance of R1 is varied from 0 to 400 ohms in the circuit of figure 6.1 and 6.2. State and explain the difference, of any, between the minimum potential difference across R2 in each circuit. Okay, so if in the first circuit, if you increase the resistance, that means that the potential difference across R2 will drop, because initially when the potential difference across R1 was 0, the resistance of R1 was 0, then potential difference across R2 was 20 as we calculated, but as the resistance got maxed out, it was 12. So meaning that resistance increases, then the voltage across R2 will decrease. And that's for the first circuit. And the second circuit, it will be quite similar as well, but the difference will be that the difference obviously will be that in this case there's a parallel combination, right? So that entails that the minimum potential difference will obviously be less. The reason for that being that the resistance here, the total resistance here, is less than the total resistance here, and resistance is proportional to the voltage. Yeah. So if you have a less total resistance, then that means that um, the voltage across it will also be lower. So total resistance of LDR plus R2 is lower than of just R2, because in the first circuit it was just R2, but in the second one it's LDR plus R2. So it's lower than just R2. So potential difference, or minimum potential difference, is also lower. Okay. Okay, so this is nuclear physics. Two isotopes of uranium are this and this. Describe in detail an atom of uranium 235. Okay. Um. Okay. Okay. So basically, you want to start describing what the things inside of the nucleus or the atom, like the proton number, electron number, neutron number, the nucleon number, the charge, if any, and etc. So in this one, you can see that proton, uh, so nucleus has like 92 protons. It also has, you just minus both of these to get the neutron number. which is like 143. Yeah. Neutrons, obviously because there's no charge, so you'll just write no charge. And if there's no charge, then the proton and electron number will be same. Has 92 electrons. Electrons around nucleus. Nucleus. And yeah, that's about it. And also you can, considering they're asking about the atom as a whole, so you could also write something that's a bit general, like the atom, most of atom is empty space. Is empty space. But this is like an extra point. These are the main ones, like that are specific to the atom itself. With reference to the two forms of uranium, explain the term isotopes. Okay, same proton number because they both have 92 / 92, but different neutron number. One of them has 143 and then the other has like 146. 143 and 146. Determine the values. Okay, so this is, what is this? Nucleon absorbs a neutron. Okay, so this is 1 and this is 0 because neutron has 1 mass and no charge. Determine the values of Y and Z. Okay, this is interesting. Okay, so you have to compare the charges or the proton number and nucleon number on both sides. So on the left hand side, the total number is 236 because the 235 plus 1 and then 92. On the right hand side, obviously because x is 0 and then this will be 1 and then multiply with 3. On the right hand side, currently there's 148 plus z plus 3 and then here it's 157 plus y plus 0. So just do a bit of calculation to find the unknown. And then 236 minus that. So z will be equals to 85. 85, and then y will be equals to like, what is this, 30, what, 35? Yeah, 35. 35. Explained by the sum of the masses of the uranium nucleus and of the neutron does not equal the total mass of the products of the reaction. Okay. They're saying why the mass is different. Right, let me just get rid of this. They're asking why the mass on the left-hand side is not the equals to the mass on the... Wait, what are they asking? The sum of the mass of the uranium and of the does not equals to the mass of the product. Oh, okay. Yeah, they're saying that the masses don't really add up. Right? They're saying that the masses don't add up. Which, yes, that's true, but that is because some of the mass is converted into energy. Right? Mass, and for these types of questions, there's just a specific pattern you have to write, which is that mass energy is conserved because in nuclear reaction, mass is not conserved because some of the mass is like converted into energy. So you say that mass energy is conserved. The total amount of mass and energy is conserved in the reaction, and then that's because some of the mass of the mass is converted to energy. Converted to energy. Such energy is released. So yeah, that's the paper.